All right. So today we will discuss something more about the functions. This lecture will cover some new features and some new different new types of functions. So first of all, we learn about the increasing, decreasing, and constant functions. Okay. Now, so far, what we know is for each and every functions, we have equations, and we can draw graphs, right? So for one graph, when you have a graph for a function, we can find or we can identify whether the graph is increasing or decreasing or a constant graph. How can we do that? For example, look at the first graph, okay? And let's say we know an interval. What do you mean by interval? Starting point, ending point. And within that point, within that limit, if there is a relation that for every x, y is increasing. For an example, let's look at the first graph. Let's draw it here again. Look at the first graph. The first graph is, so this is our intervals. You see the open dots. These are the intervals. And now let's say we claim that between this interval the graph is increasing. Now what does it mean? That means that if you choose any 2 point here, okay, and let's say the first point and second point both has x and y's, right? I'm saying they have x1, y1, or y1, y2, x1, y2. So let's write those points. The first point is x1, y1. And the second point is, let's say, x2, y2. Now, if this is the case, that you see here, x1 is smaller than x2, right? Any doubt? It will be always like that. Now, for that, if the y1 is also smaller than y2, y1 is smaller, right, than y2. Here, for an example, let me check. Okay, let's say your x is 1 here, okay? Let's say this is 1. This much is 1, 2, let's say 3, 4, okay? And here, let's start some 1, 2, 3, 4, and 5. Okay? Now look at this. For the first point, let me make it like 3, 4, okay. Now for the first point, let's say this is the x is 1 and y is 1, 2, 3, right? So for the first point, x1 is 1, y1 is 3, okay? For the second point, x2 is 4 and y2 is whatever, 1, 2, 3, 4, 5, 6. Now you see here, when the x is increasing, y is also increasing. That means, you see here, for the first point, the x1 was 1. Next point, x2 was 4, right? Similarly, y was also increasing. It doesn't have to have the same rate, but they are increasing. Now this has to be true for every single point within that interval. Now for an example, let's say this is the interval we claim, okay? Now within that interval, if you choose any 2 point, this property has to be matched. Then the graph can be claimed as increasing graph, or the function can be claimed as increasing function. Similarly, decreasing will be the reverse. For an example, if you look at the second graph, if you choose this point, for an example, the first point and the second point, you see the y is, whatever the y you have here, y is less in the next point, right? And that has to be true for every single pair of the point between that interval. What we are saying that, for an example, you have an interval, okay? And that property is matched for one pair. But that property did not match for another pair of points. For an example, let's see whether we can find such a graph. Let's say this is a graph, okay? Let's say this is a graph. Now what happens? let's say somebody claim that, do you see the graph? Everyone can see the graph? Let's say this is a graph, okay? Now here, let's say this is the interval, and let's say we are trying to decide whether the graph is increasing or decreasing. Now if you pick this point and this point, you know that the graph is increasing, right? Because you know the x is increasing and y is also increasing, right? Because you see, from here to here, x is definitely increasing, and from here to here, y is also increasing. But if you pick this point and this point, what happens? Look at this. X is increasing for sure, but y is decreasing. So for this interval, I'm saying for this interval, none of the conditions match. So basically, this is neither increasing, neither decreasing. Because if it is increasing, then every single pair of the points has to have the same property. So in this case, some pair is increasing, some pairs are decreasing. Okay? So this is not true for that. And in case of the constant one, the last one, you see, doesn't matter what is your axis, y will be always same. If you check here, look at this. For every single point on this line, y is same, right? You see the y is not changing. So that is a constant function where y will never be changing for your x. So it doesn't matter what x you have, y will be always same for every single point. Remember that, for every single point or every single pair you are comparing. Now let's see whether we. So the final note is, when you are trying to find the increasing, decreasing, or constant functions, we always use the x coordinates, right? Because you know we were using the x coordinates and see for those x coordinates how the y is changing, right? Either the y is basically, let's say you pick 1x from the from the first point and the next x from the next point, and you see whether the y is increasing or decreasing. And also you are careful so that doesn't matter which pair you pick, every time that property has to be matched. Okay. Now let's see whether we can identify these. Let's say this is a graph function, and can we tell that which part of the graph, because you know this graph is a little bit tricky, because some part of the graph is looks like that is increasing, some interval is decreasing, right? So can we identify those intervals, that where the graph is decreasing or where the graph is increasing? For an example, let's say if you pick this part, let's say you pick this interval, you know, see this is a whole graph and you pick just a segment of the graph. What I'm saying is you can pick just an interval. Now let's say this is the interval, so it started from here and ended here. What is this? Is this increasing or decreasing? It must be decreasing, right? Because you see the x is increasing, but y is decreasing. Now for an example, you pick this interval, increasing, right? You pick this, increasing, decreasing. I think it's easy to visualize, right? But can you find any part where it is constant? See, maybe some point here, we are not sure, maybe a couple of points here is constant. So for an example, if you pick probably like a very small segment here, maybe that is constant. Couple of points, probably, like, you know, we don't know exactly how many points, but because, you know, this real field, there are plenty of points, you know, there is no limit of, because there are infinite points. But it's, in general, we don't know exactly which points, but if you probably pick little bit from here, little bit from here, or here, or here, they are probably little bit, they are probably constant. How about this? Which part of the graph is decreasing? Maybe this part, right? All the way up to probably here, right? That's decreasing. And again, it's starting from here. How about this one? Is it increasing, decreasing, or constant? Now, you know, anytime you are defining increasing function or decreasing function or constant function, you first have to identify the interval. Because, you know, as you have seen in the previous examples, that it's not like the whole graph is increasing. You know, it's probably one interval is increasing, other interval is decreasing, or some interval is constant. Now here, for sure that this interval or this interval or these intervals are constant, right? But can you, anyone has any doubt that they are constant? Let's say this interval, is this constant? Because you see for x is changing but y is not. Here is constant for sure, right? This is also constant. But is there any interval in this graph which is increasing? Are you sure? But you know, little bit of that definition is, you know, remember as I said that it has to be an open interval. Okay. Now, if you let's say if you take from here to here, okay. Now somebody said it's increasing, right? Can you show me where it is increasing? Which interval is increasing? From here to here, maybe? That's what I'm saying. That's what you're saying? Which part is increasing? Is there any increasing part? Or decreasing? You see, remember the definition. If it is increasing, then every single pair has to be increasing within that interval. Do you see any interval such that every single pair of the points has that relation? So there is no increasing part and decreasing part. This is only constant because you see, let's say you pick, for an example, you pick this, okay? You pick this. Let's say you pick from here. Let me see whether I can draw it. Let's say, now let's say you pick this. For an example, you pick this interval, okay? Oops. That's not the board. Let's say we pick this, okay? Let's say we pick this. Now, let's say this is the interval and we are claiming that that's increasing, right? Now, if you pick one point from here and one point from here, definitely they will satisfy that condition, right? But as we said before, that has to be true for every single pair. Now, what about if your pair is this and this point? They're not increasing. They're constant, right? So basically there is no such interval where even if we have this point and this point, then it may be true between these two segments but there is no such point. You see, this is an open interval, right? That means this point does not exist. If we have this point, then probably we could have picked these 2 points, right? And then we said, okay, between this interval, it's increasing. But otherwise, at this point, if you pick some interval between this point, maybe some point here and some point here is increasing. But how about if you pick both points from here? They are not increasing. How about if you pick both points from here? They are not increasing either. Because if it is increasing, if you pick any single pair, that has to be true. If for some pair it is true, some pair it is not, that means it is not. Okay? So basically, in this graph, we don't have any interval which is increasing or decreasing. So all the intervals you can find, they are constant. So this is a constant function. All the segments are constant. Now let's look at a little bit more. We'll talk about the relative maxima and minima. Just for now, think minima and maxima. We'll later tell you why it is relative. Okay. So here, I just skip the definition because let's understand it. I think we'll understand the definition now. So let's say you pick an interval from a graph because you know some of the graphs are like infinite graph. For an example, this one, because you know where this part will end, right? Because this is infinite, and this way this is also infinite, right? So you don't know exactly where the graph stops. So you always talk with an interval, okay? Now let's say you pick this interval, okay? Now the only graph you are looking at is this. Now here, can you find any such point where the y is minimum? You can always find that, right? For an example, let's say we are talking about this segment, which is this. So this is the point where y is minimum, right? So for that point, your x is called minima, because for that x, y is minimum. Similarly, again, if you pick a segment, for an example, you pick this much, okay, can you find a point between this to this where y is maximum? Here, right? Can it, do everyone agree that this is the point where? Yeah. So for this point, so for this point, since the y is maximum, your x is called maxima. But the reason they are called relative, sometimes people call it local, okay, because we are not considering the whole graph. We are just considering a segment of graph or an interval. That's why we are calling, okay, this is maximum. Relatively, this is maximum because this is true only between this interval. This is only true within this range, okay? Or this is only true within this locality because, within this range. Because if you probably change it, maybe let's say if you pick from this to this, you might find some other maxima, right? So that's why they are called local maxima or relative maxima or relative minima or local minima. Okay. Now let's see. Any question about this? But remember, again, let's get back to the definition because now we probably will understand the definition better. For an example, we wanted to show you an interval. For an example, let's say this is the interval. As you see, the graph is infinite, right? So let's say you pick this interval from here to here. Just looking at this graph, whatever we can see right now, we don't see the remaining part, but we just see, so far, whatever we see, this is your maxima, right? And this is your minima. Because this is the point where y is maximum, right? And this is the point where y is minimum. And sometime the question will ask you to find the minima or maxima. All you need to do is you have to find the y for that point. Now, you probably have seen that how we are representing the number here. Instead of writing xy, we are writing, let's say, what we're writing? We are writing, instead of writing xy, we are writing in this format, x, f of x. Basically, see how we're writing. We're writing a, f of a, right? The reason we write this because this means basically your y. Remember the definition of function? How we write the definition? Y equals to f of x. Since we are discussing about the functions, instead of writing y, every time where you expect y, you will see f of x. Because in this whole discussion, we assume that y is a function of x. That's why instead of writing y, you will see f of x. Or if you don't have x, for example, in this example, you have a and b because those are some points. So you write f of a, f of b, or f of x, f of whatever is replaced for x. You will see that. Any question from local minima or maxima? All right, let's go back to the next function. So here we learned some new functions. It's basically the same functions, but some new feature of the function, and based on those feature, we basically call the functions by a new name. For an example, look at the first one, even function. Some functions are called even function when they have this relation, f of minus x equals to f of x. Can you give me an example right away? What can be such an example? Say it again. Can you think of any such function where f of x and f of minus x will be same? What do you mean 0, 0? The function is an equation, right? I'm saying, for an example, let's see. X squared is a good example, yeah. Because look at this. If the function is x squared, now what happens? Let's say you are trying to find f of minus x. So all you are doing is you are replacing x by minus x, and it will be still x squared, right? So this is an even function because f of x and f of minus x are equal. We can find a lot of different examples, but this is one of the example that hit my mind right away. But okay, now how about an odd function? Look at the odd function. F of minus x equal to minus f of x. Can you think any such function right now? Okay, for an example, let me write it down. So this is an even function, right? Now let's say, can we find any example of odd function? Let's say, how about this? How about x cubed? Look at what happens. If you just do minus x, f of minus x, what do you get? Minus x whole cube, right? And you'll end up with, which is, this is minus f of x, right? Look at f of x. F of x is x cubed, right? Remember, these are examples. There are plenty of other functions which are even odds. We're just trying to show you some small, simple examples. So this is an example of odd function. All right. Any question about this? And also, the graph of an even function in which this, because every even function is like this, right? Every even function is symmetric with respect to y-axis. Now, what do you mean by symmetric? By symmetric, we mean that both sides of y-axis will look similar. For an example, let's say I draw a graph here. Probably my drawing will not be exactly perfect, but I'm trying to show you that example. Let's say here, oops, maybe this one. Okay, it's not perfect yet. Let's see. Maybe I draw the y here. Okay, now look at the graph carefully. Okay, and maybe you can get rid of x-axis. Just don't think of the x-axis right now, because it's only about y-axis. Now look at the graph carefully. Do you see the both side is same? Both side of the y-axis is similar, right? It's exactly similar. That's called symmetric. That's called symmetric with respect to y-axis. Okay? So by the property of even function, every single even function, if you draw the graph, it will be like this. I'm saying it will not be like this, but I'm saying it will be symmetric. Both sides of the graph will be same. Maybe for an example, let's say if you find a graph, I'm not sure whether we can find the equation for sure. Let's say if you find a graph like this. Let's say this is a graph. You see, about the y-axis, both sides is symmetric, right? This may be an even function. In case of odd function, if the function is odd, we always know that the odd function will always satisfy this condition. It will be symmetric with respect to origin. Now, what does it mean? What will be that? With respect to origin. So maybe the both side of origin, it's not both side. There will be all side of the origin will be symmetric. Let's see whether we can see some example. But most of the cases, you will be given some equation, maybe function, and you have to identify whether the function is even function or odd function or none of those, because there will be function which is not even, neither even nor odd. Okay. Because all the functions do not have to be even or odd. Some of the functions may be even or odd. Okay, a graph is symmetric with respect to y-axis is every point on the graph is this. Okay, so it's basically, this is another way of another way of identifying the same property. Okay, what is that? Is that with respect to y-axis, every point xy on the graph, there is also another point minus xy is on the graph. Now what does it mean? It means, for an example, if it is symmetric. Now first of all, we know that we have some graphs, and if that satisfies that property, that function is going to be even function. At the same time, you can also do this to know whether the function is symmetric. What is that? That means, for an example, if you have a point here 1, 2, there must be a point in the graph which will be minus 1, 2. That means if there is a point xy, there will be another point which will be minus x, y. Let's say there is a point, for an example, let's say there is a point 3, 4. So what is the other point you are expecting? Minus 3 or negative 3, 4, right? That must be in the graph. Because, that will be in the other side, right? Because that is symmetric. So that's the same thing, but we are just, trying to explain the same thing in a different way. Now, if the graph is symmetric about the origin, what happens? This will exactly what happens. If you have a point like xy, there must be another point which will be minus x, minus y. Maybe I can draw a graph. Maybe let's see. Let me see whether I can find an example for you. Let's say we are trying to draw a graph. Again, my drawing will not be great or exactly accurate, but I'm trying to draw something like this. Now what happens? For an example, you have a point here. Let's say this point is 2, 2. So there must be a point which will be here, right? You see what I'm saying? So this is basically symmetric with respect to origin. At the same time, this is an odd function. And this is symmetric with respect to y-axis, and this is an even function. There may be plenty of examples. This is just one which came into my mind right away. But there are plenty of examples we can probably find. Even if you just draw something like this, maybe this will be also symmetric to origin, right? Which will be an odd function. For an example, if this is like 1, 1, this will be minus 1, minus 1. Right? If the drawing is right. So, how about this? Is this an even or odd function? We know a lot of properties right now about the even and odd function, right? How about that? Just check that property, that whether this is true or this is true. For an example, if there is a xy, there must be minus x minus y if that is an odd function or symmetric to the origin, right? Or it must have this, that if there is 1, 2 or xy, there will be minus xy if that is an even function, which is true. That is an even function, but because you think that, let's say the y-axis, you see the both side of the y-axis is symmetric, right, to each other. And at the same time, you can think of like that. For an example, you see, let's say there is a point like this, which is, what is that, 6? Let's say this is 6.10, right? The coordinate, 6.10. So there must be something negative 6.10, which is maybe this one. You can probably check with a couple of pairs, and you can also see there's, but this is not. Why this is not odd function? Yeah. For an example, let's say this is, let's say to make it simple, let's say this is 2, 2. This is a little bit less than 2, but let's say this is 2, 2, okay? Now, if it is an odd function, there must be minus 2, right? Which is here. There is nothing here. So this is not an odd function. This is an even function. And also you can see this is a symmetric to y. How about we exactly, I think, we have drawn the same example. So this is an odd function. How about this? It's an odd function, right? Because what do you think? It's an odd function? It's an odd, right? Everyone convinced that this is an odd function? Okay. So now we'll see the piecewise functions. Now what is that? Now look at this. A function that is defined by two or more equations over a specified domain is called a piecewise function. Because some of the functions sometimes defined by using multiple equations, because they have different kind of behaviors in different intervals. Okay, and those functions are called piecewise functions. For an example, without just looking at equation, first of all, look at the graph. Look at the graph. You see, look here, the function look like a constant function, right? You know the constant function where x will be changing, but y will be constant for all the points. Now look at this part. It's pretty much constant. It doesn't matter what x it is, y is always same. But look at the next part. Is increasing. So that's why these kind of functions are called piecewise function, because they change their behavior from segment to segment, interval to interval. So we have to, when you are writing the equation, you basically cannot write a single equation which will be valid for the whole function. You have to write multiple equation that will be valid for different intervals. Okay. For an example, what we did is to define this function, we have written one equation for this part, and we have written another equation for this part. We have just two here, but I have seen equation where you have like 5 different function where you might have like 5 different equations. Okay. Now let's see whether we understand what it is. Now let's say here this is a function of t, for an example. T is what? T is independent variable or dependent? It's independent. It's just like x, right? Because sometimes we assume, oh, okay, it has to be x and y. It has to be x and y, but it can be something else as well. Because in real life, people define function using different terms. But it doesn't matter what it is. You will always have something independent, something dependent. It's basically t is independent variable here. Okay. Now let's see what it is. Look at that. Look at the example. It's probably a real life example. A cellular phone company offers the following plan. This is about a plan. So $20 per month by 60 minutes. Okay, and additional time cost. We always see this, right? There's a limit. Okay, after that limit, you will be charged per minute, something like that. So it's very similar to that. $20 per month by 60 minutes. So it doesn't matter how many minutes you talk, between 0 minute to 60 minutes, you will pay $20, right? That's pretty much constant. That's what exactly the graph is representing. So wherever you are between 0 to 60, you'll be paying $20. But after that 60, this is 60, right? After 60, your charge will be increasing based on how many minutes you are talking, because for every single minute, you'll be charged 40 cents. You see, this is pretty much a real life example, right? So what we did is, so it's basically the way, sometimes people try to define the function based on the context. So the reason they just wrote C of t, because it's cost of time, something like that, So that's why it's C of t. So it's 20 if the time is between 0 to 60 minutes, right? That's the condition. If 20 plus this is what? 40 cents. And how much extra minute you have? You see the extra minute? Let's say you talked about 65 minutes. So you'll be charged 40 cents for extra 5 minutes, not for the whole 65 minutes, right? So that's why we just deducted 60 from the time you talked. Because we know that for the first 60 minutes, you have a fixed charge. Okay, I'm just trying to show you that how you write the function. I'm saying, based on the context. And this part of the equation will be valid when t is more than 60. So these kind of functions are called piecewise functions. when you see different behaviors based on the context. And okay, now can you tell me, okay, these are three different y's. The first one is C of 45. Now what is C of 45 here? Can you find it from the equation? What will be C of 45? It will be 20. Now, this case, all you need to do is, this is your t, right? So look at the t first. And then based on the t, you will choose which equation will apply. Since the t is 45, you know, since it is within this range, it's a constant function, so it will be 20. Now, how about the last one, C of 90? It will fall into the second category, right, where the t is more than 60. And in this case, we are talking about the second function, right? So just try and see how much it is. All you need to do is just replace the t by 90. We're just trying to see whether we understand the piecewise function, because in case of piecewise function, an additional condition is you have to just check the condition based on the t you are given, and you have to choose which equation will apply to this case based on the t, or based on the independent variable. It will not be t always, right? It will be something else. It will be x. So and the interesting is, how about C of 60? Is it the first equation or second equation? It's definitely the first equation, right? Because you see, this is smaller or equal, right? Anything larger than 60 will fall into the second category, right? So C of 60 is still 20, right? All right. If anyone has the answer, let me check whether I can find it. So it's 30, it's $12. I think it's 32, right? Is this 32? 32, right? Yeah. All right. Now, here is another equation, or maybe another function, but two equations for the function. For sure, this is a piecewise function. Can we draw it? Can we draw the function? Look at the condition. If x is negative infinity to 3, x is negative infinity to 3, your y should be 3. I wish I could draw it because there is not a single board, but you probably will have a line like this. It's 3, right? 1, 2, 3, that's y. There will be a line like this all the way to here up to x is 3. From the negative infinity, there will be an arrow on the other side. So let's see whether I can probably partially draw it here so that I don't have to draw the whole graph. Let's see. So maybe I can. So from the negative infinity this side, it will be all the way up to here. This is a continuous line up to here. That's probably for the first equation, because that's a constant function. Y is not changing. Second part, y is changing. How it is changing? 2x minus 3. For an example, let's say, let me pick some. Let's say we pick some. We find some points. Remember how we draw the graph yesterday? We just pick some points and then pick some x's, and for those x we found the y's. Now let's say we know that for sure after this point y will be larger than 3, right? Because we know everything up to 3. Now let's say I'm sorry, not y, x. X is larger than 3. Now let's say your x is 4. Now what will be your y? Or f of x? It will be 2x minus 3, right? What will be that? that will be 2 times 4 minus 3, which will be 5, right? But what will be the point? 4, 5, right? X is 4, y is 5. So the next point is going to be 4, 5. So let's see, the 4, I wish I draw it. 1, 2, 3, 4, and the 5 is this point, right? You can probably find a couple of points like that, and you can, I'm sure that the line will be probably increasing like this. So the graph will be, let's see whether I can show you here. It may be something like this. We had it here from the negative infinity to here, and after this point it will be something like this. But in MyMATLAB, you will be given those graphs, and you can draw, pick the points, and draw the graph. Okay. So the point is, you have to find a couple of points like this. Let's say we know up to point 3, x equals to 3. We tried x equals to 4. We can try x equals to 5, x equals to 6. After a couple of points, you will guess. You will be able to guess how the lines is. I think that's an increasing function. That will be an increasing function like this. First part is constant, then increasing. It may not be increasing for every case. It might be decreasing or something else, or some other functions. Oops. Any question? All right. So, difference quotients and functions. So, for each and every function, this expression where the h is not 0 is called difference quotient. Now, at this point, we don't know anything about the difference quotient, or this is the term we just heard, right? I think some of you probably heard for something else, but we don't know exactly why we need it. Okay, we'll need it soon for doing something else, but at this point, just assume that this is a term, and for each and every function, we'll be able to find it. Now, let's see how we can find it. Now, let's say for every function, let's say this is a function you are given, which is f of x equals to x squared minus 2x minus 5. Can we find difference quotient? Now again, as I mentioned, I just want to repeat again, we will need difference quotient to find the limit of a function, but we are not there yet. So before we do that, we just first want to know how to find the difference quotient, and difference quotient is nothing but this equation. Now to do this equation, what do you need? You will need f of x, which will be given to you for sure. You will need f of x plus h, which you have to find from f of x. Just for the time being, assume that h is a parameter, and we are not, we don't know exactly what h is. I'm saying we don't know the value of x. We just assume that is h, that is a parameter. Okay. Now, for this part, what do you need to find? You first have to find the f of x plus h. We know f of x, right, which is given. Now, to know the f of x plus h, what you need to do is, in this equation, we replace x by, we did this, right? We know how to find, remember yesterday we tried to find f of x plus 2 from f of x. It's a pretty much similar thing. So what we are doing is we are just trying to find f of x plus h from f of x equation. All we are doing is replace the x by x plus h. And you know, you can probably either get it from the formula a plus b whole square, or just multiply x plus h times x plus h. And then remaining part you will get from there. So this is what you have for f of x plus h. Anyone has any question? We are not done yet. We just got f of x plus h. Now what is next? To get the difference quotient, what you need to do is, this is your f of x plus h, right? And this is your f of x. Since there is a negative sign, we still keep it inside the bracket, because once you open the bracket, signs are changed, right? and then we see how we can cancel out some of those. We may not be able to cancel, or we may be able to cancel. I'm sure we'll be able to cancel for sure in most of the cases. We cancel some of the terms, right? Let's say x square and x square get cancelled, 2x and 2x get cancelled because they have different signs. 5 and 5 get cancelled, and we are left with this much. This is what we are left with. And then we can take a common factor from the top, which is h. You see the h, we can take common factor. We know the common factor, right, for sure. Have you heard the common factor? You can take some common factor from an equation. What do? Let's say here, we can take h as a common factor because h is common in every term here, right? When you take h as a common factor, what do? You just divide everything by h and write it here. So if you divide this by h, it will be 2x, right? If you divide this by h square by h, you will get h. If you divide 2h by h, it will be only 2. So we write everything, and we just got that h, and also after that we can cancel h and h. And we are left with 2x plus h minus 2. This is your difference quotient. We'll probably do some exercise for sure. Let's see whether we can try another example here. We'll do it for sure. So let's see whether we can do this. So we have, we are given f of x, and let me give you like 2 minutes so that you can try first, and then we'll do it for you, okay? So we'll do the same, we'll follow the same steps. We'll first find f of x plus h. What we are going to do is we'll just replace x in the equation of f of x by x plus h. All right, let's see whether we can solve this. So first we will find f of x plus h, which is just replacing the x by x plus h in the original equation, right? Look at the equation. The f of x equals to 2x plus 1. We replace the x by x plus h. Now, what do we get? 2x plus 2h plus 1. So this is our f of x plus h. Now to find the difference quotient, let's write dq, difference quotient. What is the equation? F of x plus h minus f of x divided by h equals, we will write f of x plus h right now, so which is 2 of x plus 2 of h plus 1 minus, and the f of x is 2x plus 1 within the bracket divided by h. Then we will take the bracket out. 2x plus 2h plus 1 minus 2x minus 1, right? And then we cancel out 2x and 2x, 1 and negative 1, and then we'll divide it by h. Now we are left with only 2h over h, and we can cancel out the h. So the answer is only 2. Sure. Yeah, here. Now, see, all we did is, we know the f of x, right? We just replace the x by x plus h in the original equation. You see here, we have 2x plus 1, right? We just replace this x by x plus h. See, every time we did that, remember we did that, right? We found yesterday, we tried to find from f of x, we tried to find f of x plus 2, f of 2, f of 5. So we just replace the x by that value of new value of x. So this is the new value of x. So we just replace the x by x plus h. If you recall, we did the same thing in the last one, but it was a little bit longer because the original equation had an x squared term, so we have to figure it out and we have to write the formula. You know, it was a little bit longer. If you remember, what we did, look at the original equation here, x squared minus 2x minus 5. And what we did is we just replaced the x everywhere, here and here, by x plus h. We are doing the same thing, but this was a little bit easier because the original equation function was simple than the earlier one. Any question? Yeah, see, see, it depends on what you can cancel. Sometimes you might be able to cancel a lot of things, so sometimes you may not. It depends. Right now you are canceling out 2x and 2x, 1 and 1. You are only left with h, 2h. And here you have h. So you can simply just cancel the h's. But remember in the last example, we had something like this. But to cancel, we had to take a common factor. Most of the cases you'll be able to take common factor. Most of the cases you'll be able to take common factor. We just took the common factor so that we can cancel out the h in the top, and I'm saying in the denominator and numerator we can cancel those. But here we did not have to do it because it was so simple. We can just, you know, we don't have to take common factors because there is only one term at the numerator, right? So there is another example. I'm sure that you can do that, right? So only thing that you need to do is you just replace the x squared by x plus h whole square, right? Do you want to try? You just try it. All right. So you have the answer? See whether we can. So f of x plus h is x plus h whole square minus 4, which is x squared plus 2xh plus h squared minus 4, right? Then no, you see, you are replacing the x by x plus h. So you'll be squaring the whole thing because that is the replacement of x. So the next part, okay. So this is f of x over h. So let's write the equation from here. So x squared minus 2xh plus h squared minus 4 minus the original function, which is x squared minus 4 over h. And then you get x squared minus 2xh plus h squared minus 4 minus x squared plus 4 over h. Now you cancel some terms, x squared and minus x squared, 4 and 4, right? And no, that's it. Now you are left with h squared minus 2xh over h. Now what you can do is you can take some common factor at the top, right? What is the common factor? H, right? So h is the common factor, and then after taking the common factor it will be h minus 2x over h, and you cancel the h's at the top and bottom, so you'll be left with h minus 2x. This one? Oh, okay, yeah, I'm sorry. Yeah, here everything has to be positive, right? So, but is any different in the cancellation? No. So all these are positive. So it's h plus 2x or 2x plus h, because it was a plus b whole square. So everyone has the same answer? So h plus 2x or 2x plus h. All right. So let's see. There is one more function. I think you can try. So there are some more examples. But so at this point we have a little bit modification in piecewise functions, because there are some piecewise functions which are also called step functions, because their graphs form discontinuous steps. I think we have seen these kind of functions, but we did not know the name, right? We have seen some of these examples, because these are also piecewise function. Okay, these are also piecewise function, but they are called step functions as well, because they are not continuous. Why they are not continuous? Because they have some kind of disconnected part. Because you see, this is like a ladder, because you are just steps, but they have disconnection because they're not connected in some parts. So that's why they are stepwise functions. Okay, and in such cases, we for an example, what do you do is, let's say one such function is called the greatest integer function, symbolized by intx, because you know what, in case of this is a function, people sometimes think like, there is a different type of number called integers, and integers means all the whole numbers, like 1, 2, 3, 4, 5, and that function is always like discontinuous, because from, let's say, between 1 and 2 there are infinite number of real numbers. For an example, 1.1, 1.2, 1.3, 1.69, those are all missing, right, between 1 and 2. So if you have only like 1, 2, 3, 4, 5, you will never be able to draw a continuous line between them. Okay, so one such function is this, because you see here they are not continuous because they are not connected. The only way you could have connected this, if you have included these points where you have the open dots, because if this point is included, you could have drawn a line between the steps. Okay, so that's just a modification of modified version of the piecewise function, because to define this function you will still need the piecewise functions, but they are not continuous because they are not defined in every single point. Let's say here we have an example. The USPS charges 42 cents for letters, 1 ounce. For letters 2 ounce or less, they charge something else. 3 ounce, they do something else. Graph this function and then find the following charges. Now how can you draw that? How you can graph it? Look at this. We have, along this line we have the prices. Along this line we'll have what? Ounces. Now let's say we have 1 ounce, we have information for 1 ounce, we have information for 2 ounce, and 1 ounce or less, 2 ounce or less, and then 3 ounce or less, right? These are the information we have. And then the chart is, okay, now can you draw these? Now let's see whether, so I think, and can you guess what kind of function it will be? Stepwise, piecewise? I think this will be a piecewise, because there is no discontinuity. Because look at this, 1 or less. So it may be starting from 0, because the weight cannot be less than 0, right? This cannot be negative. But when it's saying 2 or less, that means it's starting from 1 to 2. It's not discontinuous. It's continuous, but behavior is different in different points. So it's basically piecewise, but not step function. Now let's see whether we can draw this. So this is a graph, let's say, and these are the prices: 0.25, 0.75, 0.50, 0.50, 0.75, and $1. And 1, 2, 3 ounces. Maybe we are done. We'll be done by 3 ounce. So the first 1 ounce, 0 to 1, we have like 42, which will be somewhere here. Maybe let's say 45, 50, 25, 37. Maybe here, right? that will be for first 1 ounce or less, right? And then for 2 ounce or less, the price will be here 59, right? So this is 50, this is 75, maybe here, and for 3 ounce or less, that is 76, which is just right at the top of the 75, maybe here. But one of the things that you should be careful about, look at this. These points are also included. They are not open dot, they are closed dot. So that's why you can draw a line here. That is probably something new to you. You can draw the line because the graph is continuous. Because this point exists and these points also exist. Okay? Because they did not mention that, 1 ounce or less, excluding 1 ounce, because you also include the 1 ounce, you also include the 2 ounce, you also include the 3 ounce, or less. So that's why none of these are open dot. All of those are closed dot. Since they are closed dot, you can just connect everything. So the graph will be like this. I have drawn those in green lines because, just to make sure that you understand that this is not a stepwise function. Because if it is stepwise function, they have to be disconnected. And some of the points must be open dots. Everything is closed dot here. So this is a piecewise function for sure, but not the special version of piecewise function. Any question? So be careful about those open and closed dots. Okay. This is let's go back. There is no open dot. That's what I said. Because, for an example, do you think this point is included? Of course, because it's 1 ounce or less. So this is the point for 1 ounce, right? It's 2 ounce or less. So everything from 2 ounce to 1 ounce is included. So none of the point is excluded. See, when you have open dot, what does it mean? It means that that point is not included. Here, every point is included. So you will be able to draw something like this. So this is just like the ladder steps, and just like ladder, including that this is a continuous graph. So be careful about that. There is a difference, right? Because every time you have seen those disconnection, there were those open dots, right? That's why that was disconnected. Because when you have some kind of open dots, that means your graph is not defined at this point, so you cannot connect that point. But if that point is included, you can just draw the line. So now it will be just like this. And can you define? Okay, now you have the graph. Now can you answer this question? Let's say the charge for a ladder that weighs 2.3 ounce. So what is 2.3 ounce? This 1 ounce, 2 ounce, 2.3 must be here, right? So the charge will be 76 cents. As long as you have the graph, you can define almost everything, right? Okay. Now, there is a relative minimum at x. What is that? What is the relative minimum? So first of all, this is your interval. What is the minimum? This one, right? What is -2? The right answer is C. Any confusion? All right, so these are basically the summary of everything. So I think we know this, right? So what you need to do is you have to find the f of x plus h. So all you need to do is you have to replace the x squared by x plus h whole square. And then you know the equation. We'll be able to do that. So it's summary of everything because, we just tried all of those. So this is the piecewise function. Can we evaluate the piecewise function at f of -1? Which equation will apply? There are 3 equations, right? It will be -2 because, -1 exists within this range, right? Look at this. So this is going to be your equation, and that's a constant equation, right? So it's just minus 2. So the right answer will be A. Any question? So that is the end of section 1.3, but since we are a little bit lagging behind, so let's see we can start